a deep Chilean night on July 1st, 2025, the Atlas telescope detected something unusual. Among the billions of points of light its cameras register every night, one was moving wrong, too fast, too strange. The trajectory didn't match any asteroid or comet in our solar system. Automated algorithms, written to search for exactly these kinds of anomalies, sounded the alarm. Within hours, humanity received confirmation. We had a visitor from interstellar space, the third in all of recorded history. The object was designated 3I Atlas, the third known interstellar traveler, named after the system that discovered it. And from the very first days, it began showing signs that made astronomers around the world stop and think. Write in the comments where you're watching this video from and what time it is for you right now. It's important for me to understand who's interested in these stories that are unfolding right now, above our heads, while we sleep. The comet glowed green. This in itself isn't unique. A green coma often indicates the presence of diatomic carbon, a molecule that fluoresces in exactly this range under sunlight. But when the first spectral data started coming in from large telescopes, it became clear. 3. Atlas wasn't just a green comet from another star system. It carried within it a chemical mystery that challenged everything we knew about cosmic objects. Astronomers noticed something that shouldn't have been there. Lines of nickel glowed in the spectrum. Pure nickel, without iron. This was so strange that the first researchers decided there must have been an error in the equipment calibration. To understand the scale of this anomaly, you need to remember what normally happens with comets. When an icy body approaches the sun, its surface begins to evaporate. Ice turns to gas, carrying away dust and microscopic particles of everything that's been trapped in this ancient ice for billions of years. In this dust, there are always metals, remnants of that primordial material from which the star system once formed. And in any natural comet, any asteroid, any meteorite, the ratio of nickel to iron is roughly the same. These elements were born together in supernovae, mixed in protoplanetary disks, froze in the same mineral grains. They're inseparable, like twins born from the same star. But 3I Atlas was emitting nickel, 4 grams per second of pure nickel, without iron, without impurities, as if someone had taken industrial nickel alloy and sent it on a cosmic flight through the interstellar void. The first weeks after discovery, astronomers double-checked the data. Maybe it's an observational artifact. Perhaps iron is there, but for some reason, its lines aren't visible in the spectrum. But the more telescopes pointed at the green spot rushing through the inner solar system, the clearer it became. No, this isn't an error. There really is a lot of nickel. There really is no iron, and it made no sense. On October 18th, 2025, Avi Loeb from Harvard University made a statement that rang out like thunder from a clear sky. Loeb is a controversial figure in the astronomical community. A brilliant astrophysicist heading several research programs, he's also known for his willingness to voice hypotheses that other scientists prefer to discuss only behind closed doors. He was one of the few who publicly suggested that Oumuamua, the first interstellar object discovered in 2017, might be artificial. Most colleagues rejected this idea as speculation. But Loeb isn't used to staying silent when data points to something unusual. This time, he was relying on data from the Keck 2 telescope in Hawaii. Spectral analysis at the highest resolution confirmed not just the presence of nickel. The analysis showed traces of nickel tetracarbonyl, a compound that's virtually never found in nature. The formula is simple: nickel and 4 carbon monoxide molecules. But the conditions under which this compound forms stably are very specific. Too specific for space. Loeb uttered a phrase that instantly spread across all scientific forums and social media. There's only one known environment where this occurs: in industrially produced nickel alloys. This has never been documented in any other celestial object. Nickel tetracarbonyl isn't just a rare molecule. It's a key component of a process called the Mond process, discovered in 1890 by German chemist Ludwig Mond. This process is used for nickel purification in industry. You take impure nickel, pass carbon monoxide through it at a temperature around 50 degrees Celsius, and the nickel transitions into a gaseous state as nickel tetracarbonyl. Then you heat this gas to 200 degrees, and pure nickel deposits on the surface. The result is perfectly pure nickel coating, used in aerospace, nuclear reactors, high-precision electronics. It's an industrial process, man-made, controlled. It doesn't happen on its own in the cold vacuum of space, but could nature create similar conditions? Theoretically, in the protoplanetary disk of a young star, where temperatures and pressures vary widely, where gases mix in unpredictable combinations, something similar could happen by chance. Perhaps somewhere in the turbulent cloud of gas and dust surrounding an alien star billions of years ago, unusual chemistry emerged. Perhaps local enrichment of carbon monoxide and nickel created a pocket where tetracarbonyl could stabilize. Perhaps this material then froze in the icy body of a comet and was preserved in it all this time while the comet drifted in interstellar darkness. And now, approaching the sun, the ice evaporates, releasing this ancient anomalous chemistry. Researchers from Keck Observatory put forward exactly this hypothesis. They didn't deny the data. Nickel tetracarbonyl is really there. But they suggested this could be natural, though extremely rare, the result of unique formation conditions in another star system. We know so little about the chemistry of planet formation in exoplanetary systems. Maybe there, where 3I Atlas was born, the protoplanetary disk had a composition vastly different from what existed in the early solar system. Maybe that star had an unusual set of elements inherited from previous generations of stars. The chemistry of the universe is diverse. What seems impossible in our cosmic backyard might be commonplace somewhere else. Loeb categorically disagrees. His argument relies not only on the presence of tetracarbonyl, but on the absence of iron. In any natural process that could create nickel enrichment, iron should be present too. They form under similar conditions, have similar chemistry, coexist in the same minerals. Even if you imagine fractionation where nickel separates from iron, this requires such specific and improbable conditions that it's simpler to assume artificial origin. He points to the application of nickel coatings in space technology. Heat resistance, protection from oxidation, long-term stability in vacuum. If you wanted to create an object capable of traveling through interstellar space for millions of years, nickel coating would be a sensible choice. The history of interstellar visitors is only beginning. Until 2017, we didn't know a single confirmed case. Then came Oumuamua, a strange elongated object that accelerated without visible gas emission, showed no cometary activity, but still changed velocity. Then, in 2019, came Comet Borisov, more ordinary, with a classic comet tail, but also arriving from somewhere beyond. And now, 3I Atlas, the third one, with a green coma and a nickel secret. Each new guest raises more questions than it answers. We're beginning to understand that interstellar space isn't empty. It's full of wanderers, objects thrown from their home systems by gravitational interactions, collisions, migration of giant planets. The galaxy is full of exiles. And among these exiles, perhaps there are those created not by stars, but by intelligence. It's a thought that's simultaneously fascinating and disturbing. Fascinating because it confirms we're not alone. Somewhere in the depths of time and space, there existed or exists a civilization capable of building objects that cross the chasm between stars. Disturbing because we don't know what these objects are. Probes, fragments of an ancient catastrophe, messages, or just cosmic debris from someone else's technological explosion that happened so long ago that its creators have long since vanished, while their artifacts still drift through the void. The silence of space keeps its secrets. Avi Loeb's statement split the astronomical community. Within days after October 18th, scientific forums turned into an arena of heated debates. Some called his conclusions premature, based on insufficient data. Others pointed out that ignoring such an anomaly would be a scientific crime. But almost everyone agreed on one thing. Nickel tetracarbonyl in a comet is really strange. So strange that it required an explanation going beyond ordinary comet models. The problem was that there were only two explanations. Either nature found a way to create industrial chemistry without industry, or we're observing the result of someone's industry. The scientific method is built on the principle of Occam's razor. The simplest explanation usually turns out to be correct. But what's simpler in this case? To assume an incredibly improbable combination of natural conditions, or to admit the existence of extraterrestrial technology? For most scientists, the former seems less fantastic, despite all its statistical improbability. We know that nature exists. We've seen billions of examples of natural cosmic objects. But alien artifacts remain a hypothesis not backed by direct evidence. Therefore, the conservative position is to search for a natural explanation to the very end, until all possibilities are exhausted. Loeb proposed flipping this logic. If the natural explanation requires too many assumptions, maybe it's time to consider the alternative. The story of Ludwig Mond and his discovery didn't start with space at all. Born in 1839 in Kassel, the young chemist was looking for a way to obtain pure nickel for industry. In the late 19th century, metallurgy was undergoing a revolution. New alloys required high purity of components. Mond worked with nickel ore, trying to find an efficient purification method. Traditional methods were expensive and produced a product with impurities. One day, he noticed that nickel reacts with carbon monoxide at moderate temperatures, forming a volatile compound. This was a breakthrough. A metal that normally melts only at 1450 degrees could be converted into gaseous form at room temperature. And then, by heating this gas, you could get back the purest nickel deposited on any surface. The Mond process changed the nickel industry. By the beginning of the 20th century, it was being used around the world. Nickel tetracarbonyl, a colorless volatile liquid with a boiling point of 43 degrees, became an intermediate product in the production of high-purity nickel. It was used to apply thin nickel films on metals, increasing their corrosion resistance. In the aerospace industry, this became standard. Turbine blades of jet engines, operating at temperatures above 1,000 degrees, were coated with nickel using exactly this method. Spacecraft that would spend years in the aggressive environment of near-Earth space were protected by nickel coatings. But this was always the result of purposeful human action, chemical production under control. No one had ever observed nickel tetracarbonyl forming on its own in nature. Defenders of the natural origin hypothesis pointed to the complexity of cosmic chemistry. Protoplanetary disks aren't static gas clouds. They're turbulent, dynamic environments where temperature can change from -200 to +2,000 degrees at different distances from the star. Pressure varies by orders of magnitude. Chemical reactions proceed under conditions impossible to reproduce in an Earth laboratory. Too large scales, too much time. Maybe somewhere in such a disk, in a zone where the temperature and concentration of carbon monoxide turned out to be just right, a process similar to the Mond reaction started on its own. Maybe the formed tetracarbonyl was captured by condensing ice and preserved in the comet's body for billions of years. This required luck on a cosmic scale, but the universe is vast. With a sufficient number of star systems, even incredibly improbable events happen. But the question of iron remained, or more precisely, its absence. Iron and nickel are cosmic brothers. They're born in the cores of massive stars in similar nuclear reactions. When such a star explodes as a supernova, it ejects both elements into space in roughly equal proportions. These elements become part of the next generation of stars and planets. In meteorites that have fallen to Earth, the ratio of nickel to iron is remarkably constant, about 1:19. In asteroids, the same picture. In comets of our solar system, the same. Even in Comet Borisov, which came from another star system, spectral analysis showed the standard ratio. This is a fundamental pattern of cosmic chemistry. To get nickel without iron requires some very efficient separation. In Earth industry, this separation is achieved precisely by the Mond process. Iron doesn't form an analogous carbonyl compound under the same conditions. When you pass carbon monoxide through a mixture of nickel and iron at 50 degrees, nickel flies away as gas while iron remains. That's the purification principle. But this requires very precise conditions: the right temperature, the right pressure, the right concentration of carbon monoxide. Too hot doesn't work. Too cold doesn't work. Too much or too little gas doesn't work. It's a delicate process requiring control. Could nature accidentally hit this narrow range of parameters for long enough to produce a noticeable amount of pure nickel? Theoretically, yes. Practically, the probability seemed microscopic. Comparison with previous interstellar guests only intensified the mystery. Oumuamua was strange, but differently. It showed no gas activity, had no coma, left no tail. Its shape, elongated, with a length-to-width ratio of about 10:1, didn't resemble any known asteroid. It accelerated as it left the solar system, as if an additional force was acting on it. Loeb suggested then that this could be light pressure, like on a solar sail, a technology we ourselves are developing for interstellar flights. Most astronomers objected. It's just outgassing that we couldn't detect. But no convincing evidence of outgassing was ever found. Oumuamua departed into the darkness, leaving the debates unresolved. Comet Borisov was almost disappointingly normal. Yes, it came from interstellar space. Yes, its trajectory indicated origin from another star system. But chemically, spectrally, morphologically, it looked like an ordinary comet. Ice, dust, standard set of organic molecules, nickel to iron ratio normal. This reassured many. Here, they said, is proof that interstellar objects don't necessarily have to be strange. Most of them are probably ordinary fragments of planet formation, ejected into space and wandering between stars. Statistically, we should see millions of such objects if we point sufficiently powerful telescopes in the right places. Borisov fit this picture. It didn't challenge our understanding of cosmic chemistry. 3I Atlas did. From day one, its green coma attracted attention. Bright, active, emitting gas with an intensity that spoke of high volatile content. This was a real comet, unlike the mysterious Oumuamua, but when spectrographs began breaking down its light into components, The picture stopped making sense. Nickel lines dominated. This itself is unusual. Normally, nickel lines are weak, lost among many other elements. Here they were strong, clear, undeniable, and there were no iron lines at all. It was like someone had taken an ordinary comet, removed all the iron from it with surgical precision, and left only nickel. Or as if this comet was made from material that initially contained no iron, which contradicted everything we knew about planetary system formation. As October drew to a close, tension in the astronomical community mounted. Every major telescope that could point at 3I Atlas did so. Data accumulated. Confirmations poured in one after another. Yes, there's nickel. Yes, there's no iron. Yes, there are signs of tetracarbonyl. Theories multiplied. Someone proposed models of protoplanetary disks with extreme carbon monoxide enrichment due to proximity to a young star. Someone talked about possible catalytic processes on the surface of ice grains that could selectively bind nickel. Someone recalled theoretical types of stars with unusual nucleosynthesis that could produce more nickel relative to iron. But each theory required several improbable assumptions simultaneously. And Loeb kept insisting on his point. He didn't speak with absolute certainty that 3I Atlas is an artificial object. He said that this hypothesis should be on the table, should be considered seriously, should be tested by observations. He called for pointing radio telescopes at the comet, searching for any signs of non-random signals. He proposed trying to launch a fast probe that could catch up to the object and photograph it from close range. We already missed this opportunity with Oumuamua. Let's not repeat the mistake. He reminded that absence of evidence is not evidence of absence. If there really is something artificial there, and we miss the chance to verify it, future generations won't forgive us for such scientific short-sightedness. The night sky over Chile, where the Atlas telescope first noticed the green dot, remained indifferent to earthly disputes. The comet continued its path through the inner solar system, emitting its 4 grams of nickel per second, keeping it secret. Every night, new photons from it reached our detectors, carrying information we tried to decipher. Each spectrum added a piece to the puzzle, but the overall picture remained incomplete, ambiguous, open to interpretation. Somewhere in observatory archives, data accumulated that might one day give a definitive answer. Or not. Nickel tetracarbonyl is a compound with a deceptively simple formula. 1 nickel atom surrounded by 4 carbon monoxide molecules arranged in perfect tetrahedral symmetry. This geometry isn't random. It reflects the quantum mechanics of bonds between metal and gas. Nickel's electrons redistribute in a special way, creating a stable configuration that makes this compound volatile at room temperature. Such volatility for a metal seems almost magical. Imagine a substance that under normal conditions should be a solid chunk of metal transforms into a colorless liquid that evaporates more easily than water. This is a violation of intuition, a chemical anomaly that turned out to be useful for industry. But for it to arise in nature, space would have had to play the role of an invisible chemist. The conditions for tetracarbonyl formation are narrow, but not theoretically impossible. You need a source of carbon monoxide, and there's plenty of that in space. The CO molecule is one of the most common in molecular clouds, in the atmospheres of cool stars, in protoplanetary disks. It forms wherever there's carbon and oxygen at the right temperatures. You need metallic nickel in fine dispersed form, microscopic grains suspended in gas. Such grains also exist. They condense from the gas phase in the cooling shells of supernovae, in the ejections of old stars. And you need a temperature in the range from 30 to 150 degrees Celsius at low pressure. Too cold, the reaction doesn't proceed. Too hot, the compound decomposes back. It's precisely this temperature corridor that creates the problem. In a protoplanetary disk, temperature drops with distance from the star along a predictable gradient. Close to a young star, thousands of degrees, where even rocks evaporate. Further out, hundreds of degrees, the zone where rocky planets form. Even further, tens of degrees, where volatile substances condense and icy bodies form. The zone where the temperature would be suitable for the Mond reaction exists, but it's narrow and unstable. As the disk evolves, it shifts, conditions change. For tetracarbonyl not only to form, but to be preserved, it needed to be quickly captured and frozen. Maybe nickel dust got into an ice grain at exactly the moment when the temperature was right, and carbon monoxide surrounded this grain in sufficient concentration. This required luck, but didn't violate the laws of physics. However, critics of this hypothesis pointed to the scale of the phenomenon. 3I Atlas was emitting 4 grams of nickel per second. This isn't traces, not microscopic contamination. If translated into long-term perspective, over months of approaching the sun, the comet could have lost kilograms, maybe tons of nickel. This meant that a significant part of its composition must be enriched with this substance, not just a random pocket of lucky chemistry, but systematic, large-scale presence of tetracarbonyl in its ice. For this to happen naturally, the entire region of the comet's formation would have to have these specific conditions for an extended time. This is no longer one improbable coincidence, but an entire chain of them. The statistical probability became so low, it bordered on impossible. The history of astronomy is full of examples where the impossible turned out to be simply misunderstood. In 1932, Carl Jansky from Bell Labs discovered radio noise coming from the center of the galaxy. No one expected space could be a radio source. Everyone thought stars only shine in the visible range. The discovery seemed like an anomaly, equipment error, but it gave birth to radio astronomy. In 1967, Jocelyn Bell discovered pulsating radio signals of incredible regularity. The team's first reaction, this is an artificial signal. They even called the source little green men. It turned out to be pulsars, rotating neutron stars. Nature created cosmic lighthouses with the precision of atomic clocks without any intelligence. These examples taught caution. Don't rush to conclusions about artificiality when encountering the unexplained. But there was another side to the coin. The history of science is also full of examples where refusal to consider radical hypotheses delayed progress. Meteorites were considered superstition until the 19th century. Scientists didn't believe rocks could fall from the sky. Continental drift was ridiculed for decades until accumulation of data made plate tectonics theory inevitable. The idea that bacteria could cause stomach ulcers was rejected by the medical community until 2 Australian doctors proved it experimentally. One even infected himself. Scientific conservatism protects against errors, but sometimes it also creates blind spots. The question is always where to draw the line between healthy skepticism and closeness to new possibilities. Loeb often referred to a principle he called cosmic modesty. The essence is simple. We shouldn't assume our civilization is unique or special in the universe. If we, having reached the technological level of the 21st century, are already thinking about interstellar flights, designing solar sails, considering the possibility of sending microprobes to nearby stars, then why couldn't another civilization that existed millions or billions of years ago have done the same? Moreover, if they were ahead of us by even centuries, their technology could be so advanced that we wouldn't immediately recognize it as technology. Arthur Clarke formulated it elegantly. Any sufficiently advanced technology is indistinguishable from magic, or, in this case, from natural processes. The argument about nickel coating had technological logic. If you want to create an object capable of traveling millions of years through the interstellar medium, surface protection is critical. Space isn't empty. It's rarefied gas, cosmic dust, charged particles. An object moving at speeds of tens of kilometers per second relative to this medium experiences constant bombardment. Even microscopic collisions at such speeds are destructive. Nickel coating provides protection, high melting temperature, corrosion resistance, ability to form dense oxide films that protect deeper layers. In Earth's aerospace industry, this is exactly why nickel is used. It would be logical if extraterrestrial engineering arrived at similar solutions. The laws of physics and chemistry are universal. But then, why is the object emitting this coating? If 3I Atlas is an artifact covered in nickel for protection, outgassing of tetracarbonyl would mean destruction of this protection. This seemed illogical, unless you assume the object is very old, damaged, perhaps even non-functional. Cosmic debris from an ancient civilization, drifting in the void so long that its creators have long vanished. Or, alternatively, this could be intentional. An object designed to leave a trace that can be detected. An interstellar beacon announcing its presence through unusual chemistry. This idea bordered on science fiction, but wasn't the situation itself fantastic? The public reacted with predictable enthusiasm. Headlines about possible alien technology spread across the internet faster than scientific papers could pass peer review. Space enthusiast forums exploded with discussions. Some built complex theories that 3I Atlas is a reconnaissance probe from an extraterrestrial civilization studying the solar system. Some suggested it's part of an interstellar transportation network, a communication node or navigation beacon. Skeptics mocked these ideas, pointing to the absence of any radio signals, trajectory changes, or other signs of activity. But the absence of such signs proved nothing in itself. Maybe the technology operated on principles we don't yet understand. Or maybe it really was just a very strange comet. The SETI program, the Search for Extraterrestrial Intelligence, had been working for over 60 years without a definitive positive result. Radio telescopes listened to the sky, searched for narrowband signals that couldn't arise naturally. Optical telescopes searched for laser pulses. Nothing convincing was found. Some interpreted this as proof that we're alone. Others said, we're just looking in the wrong place or for the wrong thing. Traditional SETI assumed extraterrestrial civilizations would actively broadcast signals, wanting to be discovered. But what if they don't? What if interstellar communication uses methods we don't suspect? What if artifacts are the only thing remaining from civilizations that flourished and faded long before humanity's appearance? These questions led to a broader discussion about the Fermi paradox. If the universe is so vast, so old, full of stars and planets, where is everyone? Why don't we see obvious signs of intelligent life? Dozens of explanations have been proposed. Maybe life is rare. Maybe intelligent life is even rarer. Maybe civilizations are short-lived, self-destruct, or go extinct before managing to spread. Maybe interstellar travel is too difficult, even for advanced civilizations. Maybe they're hiding intentionally. Maybe we're looking but not seeing because our technologies and concepts are too primitive. Each explanation had its logic, but none was proven. The paradox remained a paradox. 3. Atlas became another chapter in this long history of questions without answers. A small green point of light rushing through the solar system at a speed that was carrying it back into interstellar darkness. For weeks or months it remained close enough for our telescopes to observe it. Then it would go beyond reach, become too dim, too distant. The observation window was limited. Every clear night was precious. Astronomers around the world lined up for telescope time, submitted observation requests, tried to squeeze every photon of information from the instruments. This could be the comet of the century, or this could be the discovery of the millennium, or this could turn out to be just another cosmic oddity that would eventually get a natural explanation and fill textbooks as a curious case of unusual chemistry. But for now, there was no explanation. There was data, conflicting interpretations, passionate debates. There were scientists defending conservative positions, and scientists ready to consider radical ideas. There were enthusiasts believing this was first contact, and skeptics seeing only another media hype around an ordinary astronomical phenomenon. The truth, as always, waited somewhere between extremes, hidden in the details of spectra, in the accuracy of measurements, in the carefulness of analysis. Science moved slowly, methodically, testing each hypothesis, and the comet flew on, emitting its nickel into the cosmic void, indifferent to what the creatures on the small blue planet it was passing thought about it. The Keck 2 telescope in Hawaii, which provided crucial data to Loeb, is one of the largest optical telescopes on the planet. Its 10-meter mirror, composed of 36 hexagonal segments, collects light from an area millions of times larger than the human pupil. On the summit of the extinct volcano Mauna Kea, at an altitude of 4,200 meters above sea level, where the air is thin and transparent, this giant peers intently into space. It was here, in the October nights of 2025, that a high-resolution spectrograph broke down the light from 3I Atlas into thousands of narrow bands, each corresponding to a specific wavelength. In this rainbow of information lay hidden chemical signatures, unique patterns of absorption and emission created by atoms and molecules in the comet's coma. Spectroscopy is the art of reading light. Each element, each molecule, leaves its imprint on passing or emitted light. Hydrogen creates a characteristic series of lines. Oxygen, another. Nickel has a complex spectrum with many lines arranged in a specific order. It's by these lines, like fingerprints, that astronomers determine the composition of distant objects. But spectroscopy requires finesse. Lines can overlap, shift due to the object's motion, weaken due to low substance concentration. Interpreting a spectrum is detective work where every detail matters. And in the case of 3I Atlas, the details formed a picture that was hard to explain. The nickel lines weren't just noticeable, they dominated. In an ordinary comet, the spectrum is rich with molecules of water, carbon dioxide, methane, ammonia. Dust gives a continuum, a broad, blurred glow. Metals are present, but their lines are weak, barely distinguishable against the background. Here the proportions were inverted. Nickel lines shone brightly, clearly, undeniably. And next to them, in the spectral range where iron lines should have been, there was only background silence. Spectroscopists double-checked the calibration. Maybe the instrument is incorrectly tuned to this range. Maybe Earth's atmosphere absorbs exactly these waves. But all checks gave one result. The data is correct. There really was no iron. In parallel with Keck, other observatories were working. In Chile, where the object was originally discovered, the Very Large Telescope of the European Southern Observatory pointed its 4 8-meter mirrors at the target. In Arizona, Mount Graham Observatory connected its instruments. In Spain, the Gran Telescopio Canarias joined the observations. A global observation network was forming, where each telescope added its fragment of information. Different instruments, different methods, different research teams, but the results converged. The anomaly was confirmed again and again. This wasn't an error of one telescope, not an artifact of one method. This was a real property of the object. The international astronomical community functions through a system of circular telegrams and electronic bulletins. When something unusual is discovered, information spreads quickly. In the case of 3I Atlas, the flow of messages was intense. Each new observatory that obtained a spectrum published a brief report. Each report was discussed on forums, analyzed by colleagues, compared with previous data. A consensus of facts was forming, even if consensus on interpretation was absent. The facts were these. Object 3I Atlas has an unusual composition with nickel predominance, absence of iron, and signs of nickel tetracarbonyl. Everything else was subject to debate. Some researchers turned to computer modeling. Could you simulate conditions in a protoplanetary disk to get the observed result? Complex models were created with thousands of parameters: temperature profiles, gas densities, turbulence, magnetic fields, chemical reactions. Supercomputers ran these models, exploring the space of possibilities. It turned out that with a very specific set of conditions, extremely high ratio of carbon monoxide to hydrogen, temperature in a narrow range, certain dynamics of dust migration, you could theoretically get local nickel enrichment. But even in these extreme scenarios, the complete absence of iron wasn't reproduced. Traces always remained. Models could explain enrichment, but not purity. Another group focused on an alternative hypothesis. What if 3I Atlas isn't quite an ordinary comet, but the core of a destroyed planet? In some planetary systems, catastrophic collisions occur. Young planets, not yet having stabilized their orbits, can collide at enormous speeds. It's believed the Moon formed as a result of such a collision between proto-Earth and a Mars-sized object 4.5 billion years ago. If something similar happened in another star system, fragments could be ejected into interstellar space. Some of these fragments could come from deep planetary layers where differentiation separated various elements. In planetary cores, iron concentrates. In the mantle, more silicates and other elements remain. Maybe there are conditions where nickel could concentrate separately. This idea was intriguing, but had its problems. Planetary differentiation usually leads to nickel accompanying iron into the core. Their properties are too similar. They mix. To separate them requires even more exotic conditions. Some researchers proposed scenarios with extreme pressures and temperatures where differences in crystalline structure could lead to fractionation. Others talked about possible effects of powerful magnetic fields on molten planetary material. But all this remained highly speculative. We haven't observed such processes directly even in our solar system, where planets can be studied in detail. Extrapolating to an unknown exoplanetary system was risky. Meanwhile, radio telescopes joined the search. If there was even the slightest probability that 3I Atlas had artificial origin, attempting to detect radio signals was mandatory. Green Bank Observatory in West Virginia, one of the world's largest fully steerable radio telescopes, allocated observation time. The Allen Telescope Array in California, built partially with funding from the SETI Institute, pointed its antennas. They searched for narrowband signals, those that don't arise naturally. Space is full of broadband noise, radiation from stars, nebulae, galaxies, but a narrow band, especially if it drifts in frequency due to the Doppler effect in a predictable way, would be a clear sign of technology. Days of observations yielded nothing. The comet was silent in the radio range. The absence of a radio signal disappointed enthusiasts but didn't close the discussion. Loeb and his supporters pointed out, "Why do we expect extraterrestrial technology to emit radio signals convenient for our detection? This is an anthropocentric assumption. If the object is a probe or artifact, it may be long non-functional, or its communication means work on principles we don't know how to detect, or it's simply not intended for communication. Not every Earth satellite constantly broadcasts. Some just observe, record, exist. An interstellar equivalent could be similar. Silence wasn't proof of naturalness, just as unusual chemistry wasn't proof of artificiality. Each fact allowed multiple interpretations. The history of science shows that resolving disputes requires time and data accumulation. When pulsars were discovered in 1967, the first months were full of speculation. The regularity of pulses was so precise, it seemed artificial, but continued observations revealed details, period changes, multiplicity of sources, their distribution in the galaxy, that pointed to a natural phenomenon. The theory of rotating neutron stars explained all observations without invoking intelligence, but this required months of work, hundreds of hours of telescope time, efforts of many groups. In the case of 3I Atlas, the problem was more complex. The object wasn't staying in place but departing. Observation time was limited. By the end of October, the comet began moving away from the Sun. It had already passed the point of closest approach in late September and was now moving along the outgoing part of its hyperbolic trajectory. Each day, it became a bit dimmer, a bit farther, a bit harder to observe. Spectroscopy requires sufficient light. The dimmer the object, the longer you need to expose, the lower the spectrum quality. Astronomers knew the window of opportunity was closing. Perhaps in a month, maybe in 2, the object would become too faint, even for the largest telescopes. And then it would disappear into the depths of space, carrying its secret back into the interstellar darkness from which it came. The discussion about launching an intercept probe surfaced again and again. Technically, this was on the edge of possibility. The object was moving at about 30 kilometers per second relative to the Sun. Fast, but not prohibitive. The fastest spacecraft humanity has ever launched. Probes to the outer planets with gravitational maneuvers reached speeds on the order of 15 to 20 kilometers per second. Theoretically, with a sufficiently powerful rocket and the right trajectory, an intercept mission could be created. But designing, building, and launching a spacecraft takes years. Even in emergency development mode, minimum a year, more likely 2. By that time, 3I Atlas would be at a distance of many astronomical units, possibly beyond Jupiter's orbit, moving toward the edge of the solar system. There was also a more ambitious option. In recent years, concepts of ultra-fast microprobes accelerated by laser sail have been discussed. The breakthrough Starshot project, launched by a group of physicists and funded by Russian billionaire Yuri Milner, proposed accelerating gram-scale microprobes to 20% the speed of light using a powerful ground-based laser. At such speed, the nearest stars could be reached in decades. Applied to 3I Atlas, such technology could in theory catch up to the object in weeks or months. But the technology remained a concept. Lasers of the needed power aren't built. Probes aren't developed. This was a vision of the future, not a tool of the present. Humanity could only observe, record, analyze, but not catch up. And yet, the value of observations was enormous. Each spectrum, each photograph, each measurement added to our knowledge of interstellar objects. Until 2017, we had theory, but no data. Now we had 3 examples, 3 guests from other star systems, each with their own characteristics. Statistics were beginning to form. We could start drawing conclusions about how common such objects are, what diversity they show, what this says about processes in other planetary systems. Even if 3I Atlas turns out to be a natural comet with unusual chemistry, that itself expanded our understanding of the possible. The universe was proving to be even more diverse than we thought, and that in itself was a discovery. Avi Loeb was born in 1962 in Israel, in an agricultural community. His childhood was spent not in laboratories but in fields, where practicality and direct contact with reality shaped his thinking. He studied philosophy before physics, and this left a mark on his entire scientific approach. For him, science wasn't just data collection, but a way to ask fundamental questions about the nature of reality. When he switched to astrophysics, he brought with him a willingness to think beyond the conventional. By 2025, he headed Harvard's astronomy department, published hundreds of scientific papers, directed numerous studies. His academic status was impeccable, but it was precisely this status he was willing to put at risk when data pointed to something unusual. The Oumuamua story began in 2017 and made Loeb one of the most controversial figures in astronomy. When this strange, elongated object rushed through the solar system, showing unexplained acceleration without visible signs of cometary activity, most astronomers searched for natural explanations. Loeb published a paper mathematically showing that the object's characteristics were consistent with the solar sail hypothesis, a thin reflective surface using light pressure for propulsion. This was technology humanity itself was developing for future interstellar missions. Colleagues' reaction was harsh. He was accused of sensationalism, insufficient scientific rigor, willingness to sacrifice reputation for press attention. But Loeb didn't back down. He said, "If the data doesn't exclude a hypothesis, it must be considered, regardless of how unusual it seems." Critics pointed out that extraordinary claims require extraordinary evidence. This principle, formulated by astronomer Carl Sagan, became a mantra of skepticism. A claim about the existence of extraterrestrial technology is undoubtedly extraordinary. Therefore, the bar of proof must be very high. An unusual shape or strange acceleration didn't reach that bar. More direct evidence was needed. Radio signals, obvious structural elements, something unquestionably artificial. Loeb responded that we'll never get such evidence if we systematically ignore anomalies and refuse to study them. He created the Galileo Project, a private research initiative funded from external sources, aimed at searching for potential extraterrestrial artifacts. The project planned an expedition to search for fragments of an unusual meteorite that fell in the Pacific Ocean, and development of systems for detecting future interstellar objects. When 3I Atlas appeared with its nickel mystery, Loeb already had a reputation as someone willing to go against the tide. For some, this made his statements less weighty. "There he goes again," they said. For others, it gave them more weight. Here's a scientist who isn't afraid to ask difficult questions. Regardless of personal attitude, ignoring Keck's data was impossible. Loeb relied not on speculation, but on spectroscopy, on measurable chemical signatures. He provided numbers, graphs, comparisons with known spectra of nickel tetracarbonyl from laboratory databases. The match was too precise to dismiss. Even critics acknowledged, the observations are real. An explanation is required. Within the scientific community, groups were forming. One, conditionally conservative, insisted on natural mechanisms. Their argument was simple. Throughout astronomy's history, every anomaly eventually received a natural explanation. Pulsars turned out to be neutron stars. Quasars, active galactic nuclei. Gamma-ray bursts, collapses of massive stars. Nature is inventive. Its process is diverse. We just don't know all the mechanisms yet. Therefore, the reasonable position is to continue searching for a natural explanation, expand models, invent new theories. Artificiality should be considered only when all natural options are completely exhausted, and we're far from exhaustion. Protoplanetary disk chemistry is complex. We've observed only a few exoplanetary systems in detail. Extrapolations are unreliable. Another group, smaller in number but no less convinced, believed that systematic rejection of the extraterrestrial intelligence or technology hypothesis is itself unscientific. Science should follow data, not preferences. If data agrees with the artificial hypothesis better than with natural ones, or if natural hypotheses require too many special assumptions, the principle of economy of explanations, that same Occam's razor, should work both ways. They reference the Bayesian approach to probability. The prior probability of extraterrestrial civilization's existence may be low, but not zero. And when you get data that's hard to explain naturally, Bayesian updating should increase the probability of the alternative hypothesis. This is mathematics, not philosophy. Loeb's public lectures drew packed halls. He spoke calmly, methodically, without emotion. He showed spectra, explained why nickel tetracarbonyl shouldn't exist in comets, drew analogies with Earth technology. The audience listened spellbound. For many, this was their first contact with the idea that extraterrestrial technology might not be a distant fantasy, but a real object of observation right now. Media picked up the story. Headlines ranged from cautious, astronomers puzzled by unusual comet, to sensational, Harvard scientist claims this could be an alien probe. Journalism quality varied, but interest was universal. 3I Atlas became a topic of conversation not only in scientific circles, but at dinner tables of ordinary people around the world. Psychologists studying perception of scientific information noted an interesting phenomenon. People divided not by education level, but by thinking type. Those who thought more abstractly, who were ready to accept uncertainty, more easily allowed the possibility of artificial origin. Those who preferred concreteness and relied on familiar patterns leaned toward natural explanations, even if they couldn't formulate them in detail. This wasn't a question of intelligence, rather a question of cognitive style, and it reflected a deeper truth. Our attitude toward the unknown is shaped not only by facts, but by psychological predispositions. Some people crave mystery, others seek order. Both approaches have their value in understanding the world. Religious communities reacted differently. Some theologians saw in the potential existence of extraterrestrial life or technology confirmation of creation's greatness. If God created such a vast universe, isn't it logical he filled it with life in many places? Others felt threatened. The idea that humanity isn't unique, not the center of the divine plan, caused discomfort. But these debates had been ongoing for centuries, since Copernicus displaced Earth from the center of the cosmos. Every new astronomical discovery repeated this pattern. First resistance, then acceptance, then integration into a broader worldview. Humanity proved surprisingly adaptive in rethinking its place in the universe. Philosophers of science use the 3I Atlas case as a teaching example for discussing scientific method. How does science cope with radical uncertainty? What to do when data allows multiple incompatible interpretations? Classical philosophy of science, from Popper to Kuhn, offered different answers. Popper spoke of falsification. A good theory must be refutable, and we advance by discarding refuted theories. But how do you falsify the hypothesis of extraterrestrial technology? Absence of radio signals doesn't refute it. Maybe the technology works differently. Presence of a possible natural explanation doesn't refute it either. Possible doesn't mean true. Kuhn spoke of paradigm shifts. Accumulation of anomalies eventually breaks the old theoretical framework and creates a new one. But one anomaly isn't a paradigm. You need a pattern, multiple cases, a new conceptual structure. Discovery history showed that sometimes chance was decisive. In 1938, German chemists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons and found barium in the reaction products. This made no sense. Barium is much lighter than uranium. How could it result? Lisa Meitner and Otto Frisch understood. The uranium nucleus split, divided into smaller nuclei. This was nuclear fission, a phenomenon that opened the path to nuclear energy and weapons. The anomaly turned out to be a window into new physics. Could the nickel of 3I Atlas be a similar window? Not necessarily into technology, but possibly into new aspects of cosmic chemistry we didn't understand? Even a natural explanation, if it required new mechanisms, would expand science. Young astronomers, students, and graduate students followed developments with special interest. For them, this was science in real time, alive, dynamic, full of uncertainty. Textbooks present science as a series of ready answers, but the reality of science is questions, debates, incomplete data, competing interpretations. 3I Atlas was a lesson in how science actually works. Some students were inspired. They wanted to be part of this discovery process. Others were disappointed. They expected certainty and got chaos. But both received valuable experience. Science requires not only knowledge, but patience, willingness to live with questions until answers appear. And sometimes answers don't appear at all. Parallel to the debates about 3I Atlas, a broader discussion developed about humanity's future in space. If interstellar objects visit our system regularly, and statistics showed several should pass per year, we just don't notice most. This meant the galaxy is full of wandering bodies. Material from other star systems passes quite nearby. Theoretically, a mission could be sent to such objects, collect samples, return them to Earth. This would be a sample of extrasolar material without the need to fly light years to other stars. Some enthusiasts called this galactic mail. The universe itself delivers samples to us. We just need to learn to intercept them. The concept was attractive, technically challenging, but not impossible with sufficient funding and political will. Funding remained an eternal question. Space programs are expensive, and public support is inconstant. After the triumphs of Apollo in the 60s and 70s, interest waned, budgets shrank. The new surge of attention to space in the 2020s was connected with private companies, ambitious plans for Mars colonization, space tourism. But interstellar research remained a niche topic. 3I Atlas could change that. If the public believes there really might be something artificial there, pressure on governments and space agencies would increase. Maybe this would become a catalyst for more ambitious missions, or maybe once the hype subsides, everything will return to normal. History showed both variants. Loeb himself remained in the spotlight not because he sought fame, but because he persistently promoted his point of view. He wrote articles for scientific journals, gave interviews, spoke at conferences. His arguments were the same, but he repeated them patiently, knowing that changing scientific consensus is a slow process. He referenced historical examples, how continental drift was rejected until Wegener died without seeing recognition, how Boltzmann committed suicide without seeing acceptance of the atomic theory he defended, how Ignaz Semmelweis went mad unable to convince doctors to wash their hands. Science, Loeb said, must learn from these mistakes. Not reject ideas just because they're unusual. Test, verify, collect data, but don't reject a priori. Nights continued to follow one another. Telescopes continued observing, and the green comet continued its path through a system it would never visit again. Each photon of light reaching our detectors was a messenger from afar, perhaps from a system where the star that spawned it has died out, or where a civilization we don't know about flourishes. These photons traveled, maybe millions of years, to tell their story to our instruments, and we tried to read this story, decipher it, understand it. This was an ancient human aspiration, to look at the sky and wonder, what's there? Who's there? Are we alone? The idea of interstellar travelers wasn't new. Back in the mid-20th century, astronomers already assumed that objects ejected from their home systems must wander between stars. Jan Oort, a Dutch astronomer, proposed in 1950 the existence of a vast cloud of comets on the outskirts of the solar system. Now it bears his name. He calculated that gravitational perturbations from passing stars could eject comets into interstellar space. If this happens in our system, Oort reasoned, it must happen in others too. The galaxy must be filled with exiled comets drifting in the darkness between star systems. But detecting them was impossible. Too small, too dark, too distant. More powerful telescopes and automated search systems were needed. These technologies only emerged in the 21st century. The Pan-STARRS program in Hawaii, the Atlas telescope in Chile, the Wide Field Space Telescope, all were designed to search for near-Earth asteroids potentially dangerous to our planet. But a side effect of this constant sky scanning was the detection of objects with unusual trajectories. Computer algorithms learned to recognize movements that didn't fit solar system orbits. Hyperbolic trajectories, those that come from outside and go back, not closing around the sun. The first such confirmed case was Oumuamua in 2017. It opened the era of observational interstellar astronomy, turning theoretical predictions into observable reality. Since then, each newly discovered interstellar object added data to the emerging statistics. How many pass through our system? What's their diversity? What do they tell us about planet formation processes in other systems? Statistical models, updated after the discovery of the first interstellar objects, predicted that several such guests should pass through the inner solar system regions per year. Most are too small or dim for detection by existing instruments. We see only the tip of the iceberg, the largest, brightest, those passing close enough. Future telescopes, such as the Vera Rubin Observatory, which was supposed to begin full operation in the coming years, promised to find dozens or even hundreds of interstellar objects annually. This would turn rare exotic events into a regular part of astronomy. There would be enough data for serious statistical analysis. Questions could be answered. How typical is the chemistry of 3I Atlas? Are there other objects with nickel anomalies? Or is this truly a unique case? Uniqueness always aroused suspicion. In science, single cases are difficult to interpret. They can be an error, anomaly, result of unique circumstances, or a sign of something fundamentally new. Only repetition allows distinguishing pattern from noise. If future observations discover more objects with similar chemical signatures, this would strengthen the natural process hypothesis, meaning some mechanism produces such objects regularly. If 3I Atlas remains one of a kind even after discovering hundreds of other interstellar objects, this would strengthen suspicion that there's something special about it. But this required time, years of observations, patient data accumulation. There were no immediate answers. A parallel discussion unfolded around defining the very concept of artificial. What makes an object artificial? The obvious answer: it's created by intelligence with a specific purpose. But how do you recognize purpose in an object about which we know nothing? On Earth, we distinguish natural stones from processed tools by characteristic chip marks, symmetry, context of discovery. Archaeologists developed criteria for distinction, but these criteria work because we know what results of human activity look like. We don't know what results of extraterrestrial activity look like. Maybe their technology is so different, we won't recognize it as technology. Maybe they use biological methods, grow their ships rather than build them. Maybe the boundary between natural and artificial in their culture is blurred. Science philosopher Carol Cleland from the University of Colorado wrote about the problem of detecting extraterrestrial life and technology. She noted that we search for life as we know it and technology as we understand it because we have no other references. But the universe may be more inventive. Life on Earth is based on carbon, water, DNA. Must all life follow this template? Technology on Earth uses metals, electricity, mechanics. Must all technology be similar? Perhaps there are forms of matter organization that perform complex functions but resemble nothing on Earth. Recognizing them as life or technology would be extremely difficult. This recognition problem is one of the central issues in the search for extraterrestrial intelligence. The history of SETI searches was a history of expanding criteria. Initially, in the 60s, they searched for narrowband radio signals at 21 centimeter frequency, the so-called hydrogen line, which any technological civilization should know. Didn't find anything. They expanded the frequency range, didn't find anything. Added optical search for laser pulses, didn't find anything. Began searching for signs of megastructures, planetary-scale astroengineering projects, such as Dyson spheres that surround a star to collect all its energy. Found several stars with unusual dimming patterns, the most famous being Tabby's star, but all received or may receive natural explanations. Failure followed failure, but each failure narrowed the space of possibilities and suggested where to look next. Some researchers proposed searching not for signals, but for artifacts, physical objects left by extraterrestrial civilizations. This idea goes back to Robert Freitas, who in 1980 suggested that self-replicating robotic probes could have explored the galaxy millions of years ago. If at least one advanced civilization launched such a program, the probes should have multiplied and spread everywhere. Some could have reached the solar system, perhaps millions of years ago, perhaps now. Where to look for them? The moon offered a good place. Without atmosphere and geological activity, any artifact would be preserved for billions of years. Asteroids, Earth's Lagrange Trojan points, all these were proposed search locations. But systematic searches weren't conducted. Too expensive, too speculative. 3i Atlas offered another possibility. If interstellar space is filled with wandering objects, some of them could be probes, active or not. They pass through our system. We can observe them without needing to fly somewhere. This made artifact searching more practical. But how to distinguish a probe from an asteroid or comet? It was proposed to look for anomalies, unusual trajectories, unexplained accelerations, strange chemistry, non-thermal radiation. Oumuamua showed anomalous acceleration. 3i Atlas showed anomalous chemistry. Were these signs of artificiality or simply our ignorance of natural processes? Debates continued. Consensus didn't form. The problem also lay in the fact that artificiality criteria constantly blurred as the discussion developed. Someone said, if this were a probe, it would maneuver. 3I Atlas followed a ballistic trajectory, therefore, not a probe. But others objected, why must a probe maneuver? Maybe it's inactive, its engines long failed. Or maybe it has no engines, it's just a passive observer using gravity for travel. Someone said, if this were a probe, it would have radio transmitters. No signals detected. Therefore, not a probe. But others objected. Our probes sent to the edge of the solar system, like Voyager, also remain silent most of the time, transmit rarely. An extraterrestrial probe might use frequencies or modulation methods we don't monitor, or it might simply observe, not transmit. Critics of the artificiality hypothesis often used the argument from consequences. If we start calling every anomaly potentially artificial, we'll undermine trust in astronomy as a science. The public expects reliable, verified knowledge from scientists, not speculation. Media tend toward sensationalism. They'll inflate any mention of aliens, create false expectations, and then when a natural explanation emerges, trust in science will suffer. This is a sociological argument, not concerning the hypothesis's truth, but concerning communication strategy. Loeb and his supporters objected, science shouldn't hide hypotheses out of fear of reaction. Transparency is more important. People are smart enough to understand the difference between hypothesis and proven fact. Underestimating the public is worse than honest acknowledgement of uncertainty. Historical examples showed different outcomes. Cold fusion in 1989, the announcement of a revolutionary energy source that wasn't confirmed, did indeed damage trust. But the discovery of exoplanets, which was also initially met skeptically, eventually triumphantly confirmed and brought a Nobel Prize. The difference was in rigor of methods and willingness to admit error. Science is self-correcting. That's its strength. Mistakes are inevitable at the research frontier. What's important is detecting and correcting them. In the case of 3I Atlas, the self-correction process was in action. Multiple groups checked data, proposed alternative explanations, searched for interpretation errors. This is a healthy scientific process, even if it looked like chaos to external observers. Technical observation details were gradually published in specialized journals. Peer review took weeks or months, but preliminary versions of papers were posted on Archive, an electronic preprint archive where scientists shared results before official publication. Each new paper was analyzed by the community, mathematics checked, assumptions criticized. One researcher from Japan suggested that the observed absence of iron could result from selective photoionization. The sun's ultraviolet radiation could ionize iron faster than nickel, changing spectral lines. Others tested this idea through modeling and showed the effect is too weak to explain observations. The hypothesis was rejected, but the process itself was valuable. Idea, test, result. That's how science works. A group from Germany published an alternative analysis of the same Keck data. They used a different background subtraction method, different Comet coma model, different spectral line database. Their results confirmed nickel's presence, but differed quantitatively. They obtained lower nickel line intensity and suggested the previous analysis might have overestimated the anomaly. However, even in their analysis, the absence of iron remained unexplained. The discussion moved into methodology details. Which background model is more reliable? Which assumptions more justified? This was typical scientific dispute, where measurement precision and data interpretation were contested. Final resolution required more data, more observations, maybe with other instruments. By the end of October, discussion began about coordinating international efforts. The International Astronomical Union, the organization coordinating global astronomy, proposed creating a working group on interstellar objects. The goal: standardize observation methods, exchange data quickly and transparently, coordinate telescope time for maximum coverage. When the next interstellar object is discovered, the community must be ready to act efficiently. Quick reaction is critical. These objects pass quickly. The observation window is limited. Missed opportunities, as with Oumuamua, shouldn't repeat. The proposal met support. Organizational steps began. A new branch of astronomy was forming with its own infrastructure and protocols. The educational community also reacted. Universities began offering courses on interstellar objects and astrobiology. Students wanted to study this field. It was new, exciting, full of open questions. For a young scientist, this is an ideal situation. Entering a field at an early stage, when fundamental questions aren't yet resolved, when there's opportunity to make a meaningful contribution. Some established astronomers switched their research programs to include interstellar objects. Funding agencies began allocating grants on this topic. The institutionalization of a new research area was occurring, which was always a sign of the topic's maturity. And the green comet flew on, gradually dimming, becoming more distant and inaccessible. Each night it was slightly fainter in telescopes. Soon would come the moment when even the largest instruments couldn't collect enough light for a useful spectrum. A few more weeks, maybe a month or two, and it would disappear from view, return to the interstellar darkness from which it came. Data would remain, gigabytes of spectra, images, measurements that would be analyzed for years. Questions would remain that might never receive definitive answers. And hope would remain that the next guest from the stars would tell us more. Scientific credibility depends on reproducibility. If a phenomenon is observed once by one group, it's interesting but insufficient. When independent observers with different instruments get the same results, trust grows. By the end of October 2025, enough independent confirmations of the 3I Atlas chemical anomaly had accumulated for most astronomers to acknowledge. Yes, there's nickel. There's no iron. It's real. But acknowledging the fact didn't mean agreement on interpretation. The conservative wing insisted on patience. Give it time, new data will appear. Someone will come up with a natural mechanism that explains everything. The radical wing insisted on boldness. If natural explanations require miracles, maybe it's time to seriously consider the alternative. Between these poles was the majority, taking a wait-and-see position. The psychology of the scientific community is such that radical paradigm changes are accepted slowly and painfully. Max Planck once remarked that a new scientific truth triumphs not because it convinces opponents, but because opponents gradually die out and a new generation grows up already familiar with it. This is a cynical but often accurate observation. The older generation of astronomers, raised on the idea that the solar system is unique in its region of space, that life is rare, that technological civilizations are practically improbable, struggled to accept the possibility of artifacts. The younger generation, grown up with the discovery of thousands of exoplanets, the idea of habitable zones around other stars, pop culture filled with alien civilizations, was more open. This generational divide manifested in discussions subtly but noticeably. Sociology of science as a discipline studies how social factors influence the production of scientific knowledge. Researchers in this field noted that debates around 3I Atlas had not only a scientific, but also a social dimension. Reputation played a role. Scientists with established careers risked less proposing radical ideas than those who had already reached the top and could afford to be bold, like Loeb. Institutional affiliation also mattered. Prestigious universities gave more freedom for unconventional research. Funding sources created incentives. Government grants required conservative, reliable projects. Private financing allowed more risk-taking. All these factors interacted, creating complex dynamics that determined which hypotheses developed and which were marginalized. There was also a cultural aspect. The Western scientific tradition, dominant in astronomy, emphasizes reductionism, explaining the complex through the simple, the whole through parts. This approach is incredibly successful, but sometimes creates blind spots. Some phenomena may require a holistic approach, understanding systems as wholes rather than sums of parts. Eastern philosophical traditions, for example, always emphasized interconnectedness and context. A small but growing group of scientists of Asian origin brought these perspectives into discussions about astrobiology and extraterrestrial intelligence. They asked questions. Maybe we're too focused on searching for individual artifacts and missing systemic patterns. Maybe signs of extraterrestrial activity are distributed and barely noticeable, requiring a different way of observing. In parallel, a discussion developed about the limits of science. Are there questions science fundamentally cannot answer? Philosopher Karl Popper argued that science works through falsification. We can't prove a theory true, only show it hasn't been refuted yet. But how do you falsify the statement, extraterrestrial technology exists? Not finding doesn't prove non-existence. Maybe we're just looking in the wrong place. Maybe our instruments aren't sensitive enough. Maybe signs exist, but we don't recognize them. This makes the extraterrestrial technology hypothesis strange from the perspective of classical philosophy of science. It could be true, but it's hard to imagine how to definitively confirm or refute it without direct contact. Some philosophers proposed a more pragmatic approach. Instead of asking, "Is the hypothesis true?" ask, "Is the hypothesis useful?" Usefulness is measured by the ability to guide research, generate predictions, organize data. The artificiality hypothesis of 3I Atlas was useful in the sense that it motivated more detailed observations, stimulated development of new detection methods, attracted attention and resources to interstellar research. Even if it ultimately proves false, the process of testing it could lead to unexpected discoveries. Science history is full of examples where searching for one thing led to finding another. Christopher Columbus searched for a route to India and found America. Similar serendipities happen in science. Technical innovations stimulated by studying 3I Atlas began appearing. One group developed a new algorithm for automatically detecting anomalous spectra in large databases. Another proposed an improved method for calibrating spectrographs to detect weak metallic lines. A third worked on designing a fast spacecraft capable of launching within weeks after discovering a new interstellar object, a concept that could be realized in a few years if funding is found. These innovations had value regardless of 3I Atlas's nature. They improved astronomy's toolkit, expanded observation capabilities. Science progresses not only through answering questions, but also through developing better ways to ask them. Public interest in 3I Atlas gradually stabilized. The first wave of sensational headlines passed. Understanding settled in that there wouldn't be a definitive answer soon. Media switched to other topics, but a certain audience remained interested. Space enthusiasts, lovers of scientific mysteries, those who find beauty in uncertainty. Reddit forums dedicated to astronomy and UFOs actively discussed each new observation. Science popularization. YouTube channels released detailed breakdowns of tetracarbonyl chemistry, explained the Mond process to audiences of millions. The quality of these materials varied, but the best were surprisingly accurate and educational. A democratization of scientific knowledge was occurring. people without formal education in astronomy could follow the cutting edge of research in almost real time. Critics of this democratization pointed to the danger of misinformation. Without strict expert review, false ideas could spread as quickly as true ones. Conspiracy theories inevitably appeared. Someone claimed governments were hiding the object's true nature, that there's secret data not being published, that contact with an extraterrestrial civilization is being prepared, but elites keep it secret. These theories were predictable and mostly harmless. Though they created background noise that made serious discussion difficult, astronomers learned to navigate this environment, explaining publicly what's known and unknown, emphasizing uncertainty without excessive skepticism that could be perceived as arrogance. Artistic culture also reacted. Science fiction writers began using 3I Atlas as a plot element. One novel, written in just a few weeks in a burst of inspiration, told the story of an archaeological expedition to the Comet a century later, when humanity achieved interstellar flight technologies. The heroes found inside the object a message from an ancient civilization, long extinct, which launched such time capsules hoping someone would find them. The novel didn't claim scientific accuracy, but conveyed the emotional resonance of the theme, the loneliness of intelligent beings in the universe, the desire to leave a trace, hope for contact that may never happen. Art processed the same questions as science, but through the prism of human experience and emotions. Musicians composed pieces inspired by the green comet. One symphonic poem used spectral data to create sound patterns, frequencies of nickel lines translated into the audible range, creating an eerie, almost metallic melody. Artists drew conceptual images, a solitary object in interstellar void, covered with frost from millions of years of travel, carrying a secret that may never be revealed. These artistic responses were part of a broader cultural process through which humanity made sense of its place in space. Science provided facts, but art gave them meaning. Religious thinkers continued integrating the possibility of extraterrestrial life and technology into theological frameworks. The Catholic Church, with its long history of engagement with science, organized a conference at the Vatican Observatory. Astronomers and theologians discussed, does the existence of other intelligent beings change the divine plan? The concept of salvation, does it apply only to humanity or to all intelligent beings in the universe? These questions weren't new. Medieval scholastics debated them, arguing about the possibility of multiple worlds. But the concrete possibility of encountering an extraterrestrial civilization gave discussions new relevance. Most participants concluded that divine creation is vast enough to accommodate any number of intelligent beings, that the universality of religious principles means their applicability regardless of intelligence's origin. The Buddhist perspective was different. For traditions emphasizing cyclical existence and infinity of life forms, extraterrestrial intelligence presented no conceptual problem. The cosmology of some Buddhist texts always included countless worlds with various forms of existence. Meeting an extraterrestrial civilization would simply confirm what was already part of the worldview. Rather, questions were practical. How to apply ethical principles of nonviolence and compassion to beings whose nature may be radically different. These discussions occurred in monasteries and at intercultural dialogue conferences, rarely making Western media, but contributing to global understanding of the theme. Secular ethicist philosophers asked questions about rights and obligations. If we discover 3I Atlas is an artifact, do we have the right to study it, disassemble it, appropriate it? This is the cultural heritage of another civilization, even if it has long vanished. International space law, established by the 1967 treaty, states that space objects are not subject to national appropriation. But does this apply to artifacts? If some country or private company develops a mission to intercept and return samples or the object itself, who does it belong to? Who decides what to do with it? These questions were abstract regarding 3I Atlas, which was already moving beyond reach, but would become critical for future cases when technologies would allow physical interaction. Some lawyers proposed developing an international protocol for extraterrestrial artifacts, analogous to protocols for protecting humanity's cultural heritage. The object should be declared the property of all humanity. Its study should be conducted by an international consortium with full transparency. Results should be accessible to all. This is an idealistic position that confronts the reality of geopolitical competition. Space exploration history was a history of national prestige and strategic advantage. First satellite, first human in space, first moon landing, all were achievements of individual countries used to demonstrate superiority. Had anything changed by the 2020s? Partially. Commercialization of space added new players. International cooperation strengthened on orbital stations. But competition didn't disappear. The Chinese space program, rapidly developing in the early 21st century, expressed interest in interstellar objects. Their telescopes observed 3I Atlas. Data was published in international journals, but there were also signs of a parallel program. Articles in Chinese journals inaccessible to Western researchers due to language barrier. Mentions of developing fast spacecraft for intercept missions. A situation was forming where several countries and blocs could independently develop technologies for studying future interstellar guests. This could lead to duplication of efforts or productive competition stimulating innovation. History would tell. October transitioned to November. Days grew shorter in the northern hemisphere, longer in the southern. Observatories in Chile received more dark time for observations, Hawaiian telescopes, less. But seasonal variations were insignificant compared to the main factor. 3I Atlas was moving away and dimming. The object's brightness fell proportional to the square of distance. Doubling distance meant fourfold drop in brightness. Each week required several times more exposure to obtain a spectrum of the same quality. Choices had to be made: long exposures for good resolution or short ones for tracking changes over time. Different groups chose different strategies, maximizing the diversity of obtained data. One of the last detailed observations, conducted in late October with the Very Large Telescope, yielded an intriguing result. The spectrum showed a slight change in nickel line intensity. They became slightly weaker compared to measurements from a week earlier. This could mean nickel evaporation is slowing as it moves away from the sun, which is logical. Less solar heating, less activity. Or this could be instrumental variation, calibration error. Or, more intriguingly, this could indicate depletion of some surface layer rich in nickel, with exposure of deeper layers with different composition. If the latter, further observations could show changes in chemical profile, which would give information about the object's internal structure. But time for such observations was running out. Science and faith always seemed opposites, but in the case of 3I Atlas, the boundary between them blurred strangely. Scientists insisting on natural origin without a convincing mechanism essentially believed such a mechanism exists, just hasn't been found yet. Their position relied not on evidence of naturalness, but on faith in nature's ability to create any observable phenomena. This was reasonable faith, backed by the history of natural science explanation successes, but still faith. On the other hand, those who allowed for artificiality also operated on faith. Faith in the existence of other civilizations, in their ability to create objects crossing interstellar distances. in our ability to recognize such objects. Both sides of the debate stood on a foundation of assumptions that couldn't be definitively tested with available means. This made the debates simultaneously scientific and almost theological. Astronomer Carl Sagan wrote in his book, Cosmos, published in 1980, that humanity stands on the shore of the cosmic ocean. We've only begun to wet our toes, only felt the first waves of infinite expanse. All our space travels so far have been coastal, along the shore of our own planetary system. The interstellar ocean remained unreachable, its waters untraveled, but sometimes something washes up on our shore from the depths. A fragment, shell, bottle with a message. Interstellar objects were exactly such gifts from the sea. We could study them, try to understand their origin, wonder what they say about distant shores we cannot see. Sagan's metaphor remained relevant 4 decades later, when 3I Atlas drifted through our system, leaving a trail of questions in the minds of those who observed it. The question of motivation arose constantly. If the object was an artifact, why was it created? Research probe, the most obvious answer. We ourselves send probes to study planets, asteroids, comets. It's logical another civilization would do the same. But research probes usually have instruments, transmitters, possibly engines for trajectory correction. 3I Atlas showed nothing like that. Maybe it was ancient, non-functional, dead technology drifting for millions of years after its systems failed. Such space graves could be common, the ultimate fate of all probes that don't return home. Or maybe the object's function was so different from what we can imagine that we simply don't recognize its signs. Another possibility, unintentional origin. Not a probe, but trash. Technological civilizations produce waste. We've left thousands of tons of space debris in Earth orbit, spent rocket stages, broken satellites, collision fragments. Some of these objects will eventually fall back to Earth, burn up in the atmosphere. But if Earth had no atmosphere, this debris would accumulate forever. Now imagine a civilization conducting active space activity for centuries or millennia. The amount of debris could be enormous. Some fragments, receiving the right gravitational kick, could be ejected from the system and begin interstellar travel. The galaxy could be full of technological garbage, exceeding functional artifacts by orders of magnitude. This was a depressing thought. The first contact with extraterrestrial technology might turn out to be their landfill. There were also more exotic hypotheses. What if the object was a message, specially designed for detection? Chemical anomaly as a signal, something so unusual that any civilization with sufficiently developed spectroscopy would notice. This would be a clever way to attract attention, not requiring active broadcasting or complex technologies. Simply create an object with impossible natural chemistry and launch it into interstellar space. Sometime, somewhere, someone will discover it and understand. This cannot be natural. Someone made this. The message could be simple. We exist. We were here. Remember us. For a dying civilization, knowing its end is near, launching such messages could be a final act. Throwing bottles into the cosmic ocean, hoping someone will find them sometime, somewhere. Philosopher Nick Bostrom from Oxford developed the concept of the Great Filter, a hypothetical barrier in life's evolution that's extremely difficult to overcome. This filter explains why we don't see obvious signs of advanced civilizations in space. Either the filter is behind us. The transition from non-living matter to life, from simple life to complex, from complex to intelligent is so improbable that we're alone or nearly alone. Or the filter is ahead. Intelligent civilizations systematically self-destruct or face insurmountable problems before becoming interstellar. Nuclear war, ecological collapse, unfriendly artificial intelligence, pandemics, self-destruction options are numerous. If the filter is ahead, this is bad news for humanity. Discovering traces of dead civilizations would intensify this anxiety. Look, they tried too, and they didn't pass. But there was also an optimistic scenario. Maybe the filter is behind us, we've passed it, and now we have a chance to become an interstellar civilization. The absence of visible others doesn't mean they don't exist. Maybe they're just far away. Maybe communication is so difficult across light years that contact doesn't happen. Or maybe advanced civilizations intentionally hide, following some cosmic ethic of non-interference, observing young civilizations like ours without revealing themselves until a certain development level. This zoo, or preserve idea, has been discussed for decades. We're like animals in a preserve being studied, but not contacted to avoid disrupting natural development. 3i Atlas could be part of such observation, a probe periodically checking whether we've reached the level where we can detect its anomaly. November 2025 brought the first signs the observation window was closing. Several planned observing sessions were canceled due to bad weather. Clouds over Hawaii, unusual for this time of year, closed Keck for a week. Telescopes in Chile were working, but the object was already at the limit of their sensitivity for detailed spectroscopy. Photometry could be obtained, brightness measurement, but high-quality spectra required excessively long exposures. Astronomers began discussing when to make final observations, understanding that each night might be the last opportunity to obtain useful data. One young graduate student from Caltech proposed an unconventional approach. Instead of trying to obtain a perfect high-resolution spectrum, use multiple small telescopes for continuous brightness monitoring in different color filters. This wouldn't give chemical details, but would allow tracking any changes in the object's activity, outgassing bursts, brightness variations, rotational modulations. Such data could reveal periodicity indicating the object's rotation and shape. The proposal was accepted. A network of amateur observatories and small automated telescopes joined the campaign. Astronomy has always been a science where professionals and amateurs could collaborate productively, and interstellar objects provided an ideal opportunity for such collaboration. Amateur astronomy experienced a renaissance in the early 21st century. Digital cameras became accessible and sensitive. Medium-sized telescopes that were previously available only to universities could now be afforded by enthusiasts. Image processing software became powerful and free. The amateur community, connected through the internet, could coordinate observations globally, exchange data instantly, contribute to serious research. Some important discoveries, supernovae, comets, near-Earth asteroids, were made by amateurs. In the case of 3i Atlas, their contribution was continuous monitoring that professional observatories couldn't afford. Telescope time is too expensive to spend on simple brightness tracking. Data began arriving. Dozens of observers around the world, in the US, Europe, Japan, Australia, South Africa, pointed their instruments at the dimming point of light. The project coordinator collected data, normalized it, accounted for differences in equipment and observing conditions. After a week, enough data accumulated for preliminary analysis. The result was intriguing. There appeared to be weak periodicity in brightness with a period of about 8 hours. This could indicate rotation of an elongated object showing different area depending on orientation. 8 hours, a reasonable rotation period for a comet nucleus. Many comets rotate with periods from several hours to several days. This observation added to the object's portrait, but didn't resolve the main mystery of its chemistry. Attempts to model shape based on the light curve gave ambiguous results. The variation amplitude was small, just a few percent, which meant the object was either nearly spherical, or we're viewing it at an unfortunate angle where variations are minimal. Or variations were caused not by shape, but by surface inhomogeneity, patches with different reflectivity, possibly related to uneven distribution of nickel material. Without high-resolution images, which were impossible at such distance, precise shape determination remained speculative. The object was a point of light even for the largest telescopes. Its details were hidden by distance and size. Historians of science in the future, looking back at autumn 2025, will probably see in it a turning point, when interstellar objects stopped being rare exotica and began becoming an area of systematic study. Infrastructure was being created: observational protocols, coordination networks, specialized instruments, theoretical frameworks. Experts were emerging whose careers specialized in this topic. International working groups were being formed. Future missions were being planned. All this happened against a background of uncertainty regarding the nature of 3I Atlas. But uncertainty didn't stop progress. Rather, it stimulated it. The desire to know, the need to resolve the mystery pushed forward. In parallel, theoretical work developed on possible mechanisms for nickel tetracarbonyl formation in nature. One group of astrochemists from the Netherlands published a detailed model. They suggested that in a protoplanetary disk with an unusually high carbon-to-oxygen ratio, a so-called carbon-rich disk, chemistry could be radically different. Under such conditions, most oxygen would be bound in carbon monoxide and other molecules, leaving excess carbon. Nickel under such conditions could preferentially bind with carbon monoxide instead of oxidizing. Iron, however, has different chemical preferences and could concentrate in other phases, for example, in carbides or sulfides that don't evaporate as easily. If a comet formed from material of such a disk, it could have nickel enrichment relative to iron. The model was elegant, mathematically grounded, and publication in the prestigious journal Nature attracted attention. But critics quickly pointed out problems. Carbon-rich disks are rare. Observations of exoplanetary systems showed most disks have carbon-to-oxygen ratios below 1, like the solar system. For 3I Atlas to originate from such a rare type of system required yet another improbable coincidence. Moreover, even in carbon-rich disks, complete absence of iron and evaporation was hard to explain. Some amount should be present. The model advanced the discussion by offering a concrete testable mechanism, but didn't close the question definitively. Another group proposed a collision hypothesis. If 3I Atlas is a fragment from a catastrophic collision between two bodies in another star system, the fragment's composition might not represent the average element distribution. Collisions separate material by density and mechanical properties. One can imagine a scenario where nickel coating or a layer of one of the bodies was stripped by impact and ejected as a separate fragment. This fragment, entering interstellar space, eventually reached our system. The idea explained the anomalous composition, but required a very specific collision type and very fortunate ejection geometry. Probability was low, but not zero. Philosophically, it was important to understand that all natural explanations operated in the regime of improbable events. Yes, each proposed explanation is physically possible, but each required special conditions, rare circumstances, fortunate coincidences. When an explanation requires many improbable factors simultaneously, the overall probability becomes the product of each factor's probability, which can yield extremely small numbers. Defenders of naturalness responded, "The universe is huge, contains trillions of star systems. Even extremely improbable events happen somewhere, sometime." We observe the result of such a rare event simply because only rare events are unusual enough to attract attention. This is called observational selection effect. We notice the strange, ignore the ordinary. Meanwhile, 3I Atlas crossed Mars's orbit, heading outward. Someday in months it will pass Jupiter's orbit, then Saturn, Uranus, Neptune. In years, it will reach the outer limits of the Oort cloud. In decades, it will enter true interstellar space. In thousands of years, it will be light years away. In millions of years, it may approach another star system, where, perhaps, another civilization will notice it, conduct spectroscopy, discover the nickel anomaly, and debate its origin. Space is full of such travelers crossing abysses of time and space, silent witnesses to processes we're only beginning to understand. Lonely shepherds in remote regions of Chile, where the sky is still dark, free from light pollution, sometimes observed the night sky as their ancestors did thousands of years ago. They knew the constellations, tracked planets, noticed meteors. Some heard about the green comet discovered by the large telescopes. Invisible to the naked eye, too dim, but knowing it's there added mystery to the night sky. In ancient times, comets were considered omens, births of kings, falls of empires, great events. Modern science rejected these superstitions, but something of the ancient awe remained. A messenger from the depths evoked a primal response that rationalism couldn't fully suppress. We're still creatures looking at the sky and wondering about our place in the cosmos. By mid-November, astronomers faced the inevitable reality. 3I Atlas was slipping beyond their reach. The object was already at a distance of more than 3 astronomical units from the Sun, beyond Mars's orbit, moving at a speed that carried it farther away each day. Brightness had fallen so much that even Keck's 10-meter mirrors barely distinguished it against the star field. High-resolution spectroscopy became practically impossible. Multi-hour exposures were required, and the result was still noisy, not clear enough for reliable conclusions. Observer teams began switching to other projects, acknowledging that the active phase of studying the object was coming to an end. What remained was work with already collected data, their analysis, publication of results, model building. But the comet itself was retreating into the silence of space. The last quality spectral observation was conducted on the night of November 12th, using a combination of several telescopes. Astronomers used interferometry technique, combining light from different instruments to increase effective collection area. This was a complex procedure requiring precise synchronization and ideal atmospheric conditions. The night turned out to be exceptionally clear, the atmosphere stable. Over 6 hours of continuous observation, enough photons were collected for a medium-resolution spectrum. Results confirmed previous findings. Nickel was present, though lines were weaker than a month ago. Iron was still absent. Signs of tetracarbonyl remained, though at the limit of statistical significance. This was the swan song of the observational campaign, the last look at the chemical mystery before it dissolved into darkness. The feelings of astronomers completing observations were mixed. On one hand, satisfaction from the collected data array. They had observed an interstellar object more intensively than any previous one. There were more spectra, better time coverage, more diverse instruments used. All this created the richest database for analysis that would be studied for years. On the other hand, disappointment from the lack of a definitive answer. The mystery remained a mystery. One could argue endlessly about interpretation, but there wasn't proof sufficient for consensus. The object would carry its secret away, leaving behind only data and debates. For a scientist, this is simultaneously a challenge and disappointment. to know the answer exists but lies beyond reach. Philosopher Thomas Kuhn wrote about scientific revolutions as paradigm shifts. The old theoretical framework accumulates anomalies it cannot explain until a new framework appears that explains these anomalies and opens new horizons. But revolutions are rare. Most of the time, science does what Kuhn called normal science, solving puzzles within the existing paradigm. 3I Atlas was a puzzle, but was it revolutionary enough to break the paradigm? Most believed no. It's just a complex puzzle that will ultimately be solved within existing understanding of cosmic chemistry and planet formation. A minority, including Loeb, suggested this might be the first stone of an avalanche, the beginning of realizing that the galaxy is or was populated by technological civilizations that left traces. Time will tell who was right. Public interest gradually faded in parallel with the comet's brightness. The news cycle is merciless. Today's sensation becomes yesterday's news. By the end of November, 3I Atlas was rarely mentioned in media. Enthusiast forums continued discussions, but activity declined. People returned to their daily lives, earthly concerns. Space is vast and indifferent to our attention. Objects continue their trajectories regardless of whether we observe them or not. This indifference of the universe simultaneously liberates and oppresses. We're free to find our own meaning, but no cosmic purpose awaits us. 20th century existentialists grappled with this realization. By the 21st century, it had become almost a banality, a background state of cultural consciousness. But for some, 3I Atlas left an indelible mark. A young astronomy student in Boston, following the developments, decided to dedicate her dissertation to interstellar objects. A schoolboy in Tokyo, inspired by the green comet, decided to study chemistry, dreaming of understanding reactions that occur in space. A writer in Buenos Aires began a novel where humanity finds an encoded message in the comet that transforms civilization. A physics teacher in Cape Town developed a new lesson using 3I Atlas as an example of scientific method in action, how scientists work with uncertainty, how hypotheses are formulated, how data is interpreted. The event's influence spread in circles, touching lives in visible and invisible ways. Historical perspective suggested that the significance of 3I Atlas might be fully appreciated only after years or decades. The discovery of pulsars in 1967 seemed just an interesting astronomical curiosity. Only gradually did it become clear they became a tool for studying extreme physics, testing general relativity in strong fields, discovering the first exoplanets, investigating the galaxy's structure. Similarly, interstellar objects could turn out to be a window into processes we couldn't otherwise observe. Planet formation in exosystems, dynamics of young planetary systems, chemical diversity of the galaxy. And if at least one of them turns out to be artificial, this would fundamentally change human civilization. The question of future missions remained open. Avi Loeb's Galileo project received additional funding after the buzz around 3I Atlas. Concepts were being developed for fast-response spacecraft that could be launched within weeks after discovering a new interstellar object. One design proposed a small probe with a solar sail, accelerated by ground-based laser, technology being developed for the Starshot project. Adapted for solar system internal purposes, it could reach speeds sufficient to intercept fast-moving objects. Another concept used a nuclear pulse engine, controlled nuclear explosions to create thrust. The technology was theoretically developed back in the 60s under the name Project Orion, but never implemented. Interstellar objects gave new motivation for reviving these ideas. The European Space Agency began a preliminary study of the Interceptor mission, an automatic probe that would constantly remain ready in Earth orbit, capable of launching toward a new interstellar object with minimal warning. The cost was estimated at several billion euros, making the project difficult to approve amid competing priorities. But public interest in 3I Atlas showed that support for such missions exists. Politicians are sensitive to public opinion, and if enough people believe studying interstellar guests is important, funding can materialize. Experience showed that ambitious space projects require not only technical solutions, but political will, which often depends on the cultural moment. The cultural moment of the late 2020s was specific. Humanity faced multiple challenges: climate change, geopolitical instability, technological dislocations from artificial intelligence and automation. In such context, space exploration could seem like a luxury, a distraction from pressing problems. But there was another perspective: space as a unifying force, as a reminder that all humanity shares one small planet in a vast universe. The famous photograph of Earth, taken by Apollo 17 in 1972, the blue marble against black void, played a role in the rise of ecological consciousness. Maybe interstellar objects could play a similar role, reminding us of our connection to the broader cosmos. Literature and cinema always explored themes of contact with the extraterrestrial. From H.G. Wells's War of the Worlds to Carl Sagan's Contact, from Close Encounters of the Third Kind to Arrival, human imagination returned to this theme again and again. The pattern was recognizable: initial detection, attempts at communication or understanding, conflict or transformation. The reality of 3I Atlas didn't fit these narratives. There was no dramatic contact, message, conflict. There was only a dim point of light with an anomalous spectrum, slipping into darkness, leaving more questions than answers. This didn't make the story less significant. It was just a different kind, not drama, but quiet mystery, requiring patience and humility before the unknown. Religious communities continued integrating the possibility of the extraterrestrial into their worldviews. Islamic scholars pointed to Quran verses mentioning the multiplicity of Allah's creations. And among his signs is the creation of the heavens and earth, and what he has dispersed throughout them of creatures. This was interpreted as allowing for life beyond earth. Jewish tradition, with its emphasis on the infinity of divine creation, also found room for multiplicity of worlds. Hindu cosmology always included countless worlds and levels of existence. For most religious traditions, studied in their depth, extraterrestrial life presented no theological problem. Problems arose rather in popular simplified versions of religions, where Earth was considered the only place of divine attention. The last photometric observations of 3I Atlas were conducted at the end of November by a network of automated telescopes. By this time, the object was at the detection limit even for photometry. The light curve collected over 2 months confirmed periodicity of about 8 hours, though amplitude was small. This allowed a rough estimate of shape, probably an elongated ellipsoid with axis ratio of about 1.5 to 1. Not extremely elongated like Oumuamua, but not spherical either. Normal shape for a comet nucleus. Size was estimated from albedo and brightness, probably several hundred meters in length. A small object by cosmic standards, but large enough to retain volatiles during interstellar travel. All these parameters had large uncertainties, but gave at least some idea of the guest's physical characteristics. By early December, 3I Atlas effectively disappeared from observations. Distance exceeded 4 astronomical units. Brightness fell below the threshold even for the largest telescopes for useful observations. Theoretically, the James Webb Space Telescope could still distinguish the object. Its infrared instruments and huge mirror area gave the ability to observe extremely faint objects. But telescope time on Webb was precious, allocated years in advance, competition for it incredibly high. Requests to observe 3I Atlas were submitted, but didn't receive approval. The committee decided the scientific return didn't justify the time. The decision was rational from the perspective of maximizing scientific output, but many regretted the missed opportunity. Maybe infrared observations would have revealed something new, some detail that would resolve the mystery. Now this remained in the realm of the hypothetical. Winter was arriving in the northern hemisphere, summer in the southern. Life continued. People prepared for holidays, finished annual projects, made plans for the future. The sky above cities was hidden by lights and smog, but in dark places, deserts, mountains, remote islands, stars shone as always. Somewhere there, in the direction of the constellation that slowly shifted as the object moved, 3I Atlas continued its run. Invisible, forgotten by most, but still existing, still traveling. In a year, it will be beyond Jupiter's orbit. In 5 years, beyond Neptune's orbit. In 1,000 years, light months from the sun. In 1,000,000 years, it may pass by another star, begin a new cycle of possible observations, new questions. Space is patient. Journeys are measured not in years, but in epochs. The silence that followed 3I Atlas's departure from telescope view was special. Not the empty silence of absence, but the filled silence of an unresolved mystery. In observatory archives around the world, terabytes of data were stored, spectra, images, photometric series. Researchers continued working with this material, extracting details, building models, publishing papers. But the object itself, the source of all this data, was already unreachable. It continued its path through the outer solar system, slowly fading, cold, returning to the state of interstellar rest from which approaching the sun briefly roused it. Activity ceased. The green coma dissipated. Nickel evaporation stopped. What remained was just a dark rock hurtling through the void at a speed that would carry it beyond human reach for centuries ahead. In January 2026, the first major review article about 3I Atlas was published. A collective of 57 authors representing 23 countries gathered all observational data, all proposed hypotheses, all explanation attempts. The article took 40 pages in the Astrophysical Journal, the most prestigious publication in this field. Conclusions were cautious, carefully calibrated. The object shows unusual nickel enrichment and iron deficiency inconsistent with known comet chemistry models. Presence of nickel tetracarbonyl is probable, but not absolutely confirmed due to noise in the data. Natural mechanisms capable of explaining observations require special conditions and further theoretical development. Alternative explanations, including the possibility of artificial origin, cannot be excluded based on available data. Further observations of future interstellar objects are required to build statistics and more reliable conclusions. This was the language of science, precise, cautious, refusing to make categorical statements without sufficient grounds. But between the lines was an acknowledgement. We don't know. We collected the best data we could. We applied the best analysis tools. We engaged the best minds. And still, the mystery remained. This wasn't defeat. It was honesty in the face of the unknown. Science progresses not only through answers, but through the right questions. 3I Atlas posed questions that would guide research for years ahead. What is the chemical evolution of protoplanetary disks in different star systems? How are comets formed and ejected in other systems? How often do catastrophic collisions occur that produce fragments with unusual compositions? Can a technological civilization leave artifacts recognizable across interstellar distances? Each of these questions opened entire research directions. Avi Loeb, in a February interview, said a phrase that became quoted: "We live in an amazing time when the universe is beginning to deliver samples right to our doorstep. Wisdom is not turning away from the door when the knock is unusual." His critics objected that the knock might just be wind. Not every unusual sound means a guest. But the metaphor resonated with the public. The idea that space actively communicates with us through these wandering objects had poetic power, regardless of literal truth. Human consciousness works through stories and metaphors as much as through data and equations. Both forms of knowledge have their place. By spring, interest in 3I Atlas in public consciousness transformed into something else. The object became part of cultural memory, a symbol of unresolved mystery. Mentions appeared in unexpected places. A poet included lines about the green comet in a collection about loneliness and connection. A composer wrote a minimalist piece for piano titled 3I Atlas, where repeating patterns represented the object's rotation and dissonances, its chemical strangeness. An educational program for children used the comet as an example of scientific process, showing that not all questions have quick answers, that uncertainty is a normal part of discovery. The object ceased being just an astronomical phenomenon and became part of the broader cultural landscape. The history of human knowledge is a history of gradual horizon expansion. Once the horizon was the edge of visible land, then it became the boundary of explored seas. Then it extended to the solar system's planets. Now it was beginning to include interstellar space. Each expansion brought new discoveries and new mysteries. Each required new tools, new ways of thinking, new methods of interpreting observations. 3I Atlas was a milestone in this expansion, not because it resolved old questions, but because it showed the scale of what we still don't understand. Space proved to be stranger, more diverse, more full of surprises than even optimistic scenarios assumed. Planning for future observational programs took into account the lessons of 3I Atlas. The Vera Rubin Observatory, which began full operations in 2026, was programmed for automatic detection of objects with unusual trajectories. Its wide field of view and sensitivity promised to find dozens of interstellar objects annually, creating a statistical sample. Fast alert protocols were being developed. When a new object is discovered, information instantly spreads through a global telescope network, allowing observations to begin before the object becomes too dim. Databases were being created to collect and standardize all observations, making information accessible to researchers worldwide. The infrastructure of interstellar astronomy was being built systematically, turning rare events into a systematically studied phenomenon. Some young scientists, inspired by 3I Atlas, chose unusual career paths. One graduate student decided to specialize in astroarchaeology, a hypothetical discipline studying potential artifacts in space. This was a risky decision. The field barely existed. Chances of finding something real seemed minimal, academic prospects uncertain. But she argued, someone must be ready if an artifact is actually discovered. Someone must develop methods, criteria, theoretical frameworks in advance so as not to improvise at the moment of discovery. Her courage evoked admiration in some, skepticism in others. But diversity of approaches has always been science's strength. Debates about 3I Atlas gradually quieted, but didn't disappear. Periodically, a new paper appeared offering refined analysis or alternative interpretation. Each met criticism, defense, further discussion. The scientific community slowly moved toward consensus on some aspects. Yes, the object was unusual. Yes, its chemistry went beyond standard models. But on the main question, consensus didn't form. Natural or artificial? Most leaned toward natural explanation by default, having no better alternative. A minority continued insisting the question remains open. This is the normal state of science at the frontier, not unanimity, but multiplicity of perspectives competing for explanatory power. Somewhere in the depths of space, far beyond Mars's orbit, accelerating toward the outer planets, 3I Atlas continued to exist. The object didn't know about the debates it caused, wasn't aware of human telescopes that tracked it, human minds that tried to understand it, human hopes and fears it catalyzed. If this was a comet, it simply was a comet, an ancient piece of ice and rock, witness to another star system's formation, accidentally cast into interstellar space, accidentally passing through our system. If this was an artifact, its creators long vanished, their civilization turned to dust epochs ago, and their message traveled without recipient, perhaps for millions of years. Both scenarios are equally lonely, equally poignant. A natural object, silent witness to cosmic processes, or technological silent monument to extinct intelligence. The night sky continued rotating above Earth, as it had rotated billions of years before the first humans looked up and wondered. Constellations slowly shifted through Earth's axial precession. Planets moved in their orbits, appearing and disappearing in morning and evening skies. Meteors traced fleeting lines of light. Satellites, creations of human hands, glided like slow stars. And somewhere there, invisible, untrackable by ordinary means, 3I Atlas receded farther, second by second, minute by minute, hour by hour. Each moment added kilometers to the distance. Each day carried it farther from the only beings in the known universe who noticed its strangeness and tried to understand. Ultimately, 3I Atlas left behind something more valuable than answers. It left a reminder that the universe is larger than our theories, that between known and unknown, the boundary constantly shifts but never disappears, that every answer births new questions, every discovery opens new horizons of the unknown. That humility before cosmic mystery is not weakness, but wisdom, that the ability to say, "we don't know," is as important as the ability to say, "we know." That the quest for understanding is a journey without final destination, but value lies in the journey itself, in the process of knowing, in moments when the curtain parts and we glimpse something new, even if we don't fully understand it. People continued living, working, loving, dreaming under a sky that held countless secrets. Most didn't look up often, absorbed in earthly affairs. But sometimes, on a quiet night in a dark place, someone raised their gaze and saw the stars, and maybe remembered the green comet that passed this way, and maybe wondered, what else is there in the depths? Who else looks at their sky from other worlds, sees other stars, asks the same eternal questions? Are we connected through these questions to other minds, even if we never meet, separated by insurmountable distances and times? Or are we alone, the only witnesses of our own existence, the only way for the universe to become aware of itself in this corner of infinity? There were no answers. There were only stars, silent and distant. There was only space, vast and indifferent. There was only mystery, deep and impenetrable. And there was hope that someday, maybe not in this generation, maybe not in this century, but someday we'll know more. That the next guest from the stars will tell its story more clearly. That patient accumulation of observations, slow construction of understanding, persistent application of scientific method will ultimately lead to illumination. Or that, in the most unexpected turn, contact will happen when we least expect it, changing everything. Until then, all that remained was to observe, to wonder, to build better instruments, to look farther, to think deeper, and to maintain readiness to be amazed, because the universe, as 3i Atlas showed, is always ready to surprise those attentive enough to notice.